So recall that a second order linear homogeneous differential equation with constant coefficients has the auxiliary equation that we see here, and that when we solve it, we are left with three different cases depending on what's inside the square root. And here we'll consider the case where b squared minus 4ac is strictly positive, and so that we get two distinct real roots. So this is the case that we consider first, and the distinct real roots are what's found here, 1 and 2, depending on whether you choose a plus or minus. Okay, so one solution will have a plus and the other a minus. The general solution then will be given here, okay, where m1 and m2 are as we solve. Okay, and we know this is the general solution because when the exponential has different constants in there, then they're linearly independent. We have proven that before by looking at the Wronskian. So let's look at an example. We want to solve the differential equation that we see here. Is it linear? Yes. Is it homogeneous? Yes. Does it have constant coefficients? Yes. Okay, and then from there we could get the auxiliary equation. We don't have to, guess the general form e to the mx and plug it in, and then, we've already done that work to get the general auxiliary equation. All we have to do is just remember that we got to take this coefficient and multiply by m raised to the power 2, because that's the coefficient in front of the second derivative. The coefficient in front of the first derivative will have, and we don't forget the minus, be multiplied by m to the power 1. Okay, that's the first derivative. And m to the power 0 is the same coefficient as in front of y to the 0th derivative, if you will, just the function itself. Well, we get this quadratic equation. Okay, it's a polynomial. We solve it by factoring. Okay, we could just kind of guess what the factors would be, and we end up with these two factors. Okay, and so this is 0 if this is 0 or this is 0. Okay, and so that we get these two solutions. M is equal to -1/2 corresponds to here. If you put -1/2 in here, you'll get 0. If you put 3 in here, you'll get 0. And there goes our two distinct roots, and so the general solution will follow this form. Okay, except now we have c1 times -1/2 times x, corresponding to the first root, and e to the 3x corresponding to the second root, and we are done. There goes our general solution to this homogeneous differential equation there.